A very simple thing to do with an architecture of the cache is instead of having a single data word, have some power of 2 number of data words. So I can have, in this case, a 4-word block associated with each tag. I'm going to use now I'm going to replace this picture here with sort of B bits here, which will determine which word of the block I'm trying to access. Okay, and then this is the cache index, like so. So now I'm using the address in a slightly different way. I'm still using some field of it here to select which cache line to look in my n-way set associative cache. But I'm going to use a small number of these bits. In the case of a 4-word block, I'd be using 2 of them, okay, to amortize the cost of the tag over a bigger amount of data. Block caches are actually really neat. Why? Because when you think about how instructions work, if I'm going to execute the instruction that's in that location, with high likelihood, where's the next instruction going to live? At PC plus 4. So you can imagine that caches that are block caches are particularly good at instructions. I'm not increasing the amount of tag hardware or anything. All I'm really doing is making it so that if I'm going to access one element in a block of data, I'm likely to access the next element. So for small block sizes like 4 or 8, that's pretty good. You know, you can't take this too far. If you make the block be 2 to the 16th words, now, you know, chances are you'll be, put a lot of energy to bringing all those words in, okay, into the cache, and then only access a small portion of them. But for small blocks, it's usually the case that the cost of bringing them in will be paid back because you'll almost certainly be accessing them. Okay, now remember that because of the way this cache is organized, if one word in the block is there, all the words have to be there. In other words, remember the tag isn't telling me which pieces of the data are there. The tag is either says it's all here or it's all not. So I'm going to pay the cost of bringing in 4 words and hope that it's paid back. Okay, so the other thing that's nice about this, in a memory system that has a high latency but a good throughput, is that we have to pay a lot to get that first word, but the next words will come a very small number of nanoseconds later because of the pipeline nature of the memory system. So we're able to bring in a lot of different words in a row here very quickly. So typically we have a wide path from memory, and then we can use the pipeline nature of our synchronous DRAMs or DDR RAMs to actually fill up words very quickly. Yes?
So I'm not sure I understand what exactly the blocking is.
The blocking is basically saying instead of having only 1 data word for the tag, I'm going to have 4 or 8 or 16 data words per tag.
So the tag, instead of identifying, are you just like...
The tag is still identifying the address of each of those locations. It's just that it's identifying the address of a block of, in this case, 4 locations. Okay. So
it's going to like ignore the lower several other bits.
right. So there are some bits that are going to be of the address that are now being used to select the word within the block. Right. And the address of the block now has correspondingly fewer bits in it. You get a sense by looking at this picture of how the addresses in the blocks go. So everything is blocked, right? So nowadays we have 4 and 16 word blocks, but not much bigger than that. Okay, I'm going to stop here.